Hello, yes, so my name's Matthew Martin, I'm team leader, master control room. I think I need to explain what it is. I think John's done a very good job, so move straight on. This project is inspired by an issue we've had. We provide, if you know the local radio stations for the BBC, in the daytime, there's 30 odd of them, they're all doing their own programmes. At night time, they all fold back to Radio 5. Master control room, we provide the feeds of Radio 5 to our sister department, coding and mux, and there's an automatic switch which overnight changes the audio to 5 Live. This is the circuit, basically, of the 5 Live. Comes in from Salford to ours, there's a 2x1 switch, an audio router which belongs to CCM, goes into AES67, some more routing, and to the transmitters. We've got monitoring points, both ends. The issue we've got is occasionally something in that chain goes wrong. And when it goes wrong, it makes the audio sound awful, and it makes it sound awful in a way that we didn't have anything that could detect it. So the first time we would know is when people who can't get to sleep phone up and go, it sounds awful, and then they phone us up, and then it's a simple fix. You basically reboot that 2x1 switch, and it all comes good again. So it would be nice if we could actually detect it, because it's probably going wrong in the daytime and no one's noticing to nighttime. So if we could detect it when it goes wrong, then we can reboot it in the daytime and it's all good. We can't replace the switch because it's made bespoke by someone in his shed and he's retired and the usual thing. So we thought, could we create some sort of analysis tool which could take the inputs and the outputs of this chain and say whether it's going to work or not. So the first thing we did, which you have to do with any sort of machine learning thing, is you have to get some data and visualize and analyze your data. So we took some recordings and we ran it through this bit of open source software. I'd recommend it to people, partly because I wrote it. So this bit here, this takes the input and the output, turns it into the frequency domain, minuses off the two, and shows you the difference. So you sort of get the frequency response to the circuit. So this is the 5 Live working circuit, which I can play. So the red line is basically showing you the average difference. So it's pretty flat, which you'd hope, because there's not much active kit in there. The grey is the sort of the momentary. So it sounds fine, it looks fine. We've managed to get also some recording of when it's broken. You can see before I play it, it looks a bit weird.
Agency workers. One agency worker, Mark Kenneth Baldwin, said when he found out he'd been sent to replace SAP staff, he quit. I've got kids.
So you don't really want that going to air? I think basically what's happened is a 2x1 switch has told the router, I'm sending you 24K. And the router's gone, oh, I'll put some sample rate converting in there then. And therefore the high frequencies have all got boosted. But the question was, could we develop a machine learning project, a model which can learn basically that momentary frequency response, and then if that model's outputs don't match what we're seeing, we can have an alarm and someone can listen and reboot the box. So, what do I mean by machine learning? I'm just going to go through it quickly for those that are not completely across it. Basically, machine learning model, when I'm talking about it here, it's a mathematical formula or algorithm, and you present it with your input data, and it goes through this algorithm, and it produces your output data. And what you do is you first of all give it a load of data, which is where you know the input and the output, and you train the model so that the errors that it produces get minimized. And you just keep running it, and you keep running it, and until you've got, it's made itself, the algorithm has made itself so that the loss function, the errors at the end are as small as possible. There's 2 main types of machine learning. We've got regression, which is trying to basically find the best line of best fit. Anyone who's done their science at school, you have your data and you draw the line which looks best if you hit your data. What you're actually doing is you're minimizing basically the mean square error, which is the error between the blue line and the vertical red dots. And we can do that in 2 dimensions like that, or you can do it in multiple dimensions. So you could have it in basically finding a hyperplane rather than a line of best fit. That works for continuous data. The other one you've got is your classification. Your classic, is this a picture of a cat or a picture of a dog? Or maybe is this audio good or this audio bad? So that might seem the one to choose. The problem is, in order to do that, you have to present the model with lots of bits of good audio and lots of bits of bad audio. And luckily, we don't have lots of bits of bad audio. We've got lots of good audio and we've got a few bits of bad audio. So what we decided to use was the regression model. And basically, we're going to use that model to predict output frequencies depending on input frequencies. And then we're going to compare those output frequencies that it's predicted with the actual ones. And that was going to give us an error. And if that, as long as it can do the predictions well so that when it's working, the error is low, then we can assume when the error goes high, it's not working. Just for fun, let's make it run on a Raspberry Pi. We don't want to be using GPUs, we don't want to be sending it off to Amazon and giving them money, so let's make it run on a Raspberry Pi, and then we can put it anywhere. And we've already got some software which does audio monitoring, which we wrote in the control room, so why not make it work on that? So that's basically just saying what I said there. Then, of course, we had some scope creep, and someone said, oh, if it would work for that, maybe it would work for a more complex circuit. Maybe it would work to monitor the whole of a broadcast chain. So this is the Radio 1 TX chain from a studio, a couple of routers, load of processing, as you'll know if you've listened to Radio 1, some more switches, DAB encoding, currently MP2, very lossy, transmitter, and then to complete the circuit, we have some check receivers, so some MP2 decoding, and those are our 2 monitoring points. So we could make it learn that as well. That would be very cool. It's a lot more complicated. So again, let's take some recordings and visualize it. So this is a working Radio 1. Which, as you could see, wasn't as flat anymore. It's all over the place, and it's also, that previous one, the red line stayed pretty still. The average was there. On this, the rolling average it's constantly changing. And this is a pretend faulty one. I couldn't find any, at the time, bad recordings of Radio 1 going to air, which was quite good, really. So I took a good one, and I basically stuck in some hard clipping at 6 dB, neg 6 dB. So you can't really hear it. It is there if you listen carefully.
We can make some bread, we can split a check, but I ain't back and forth on the internet.
Enough of that. So the question is, I mean, it's sort of there, but if we can make it detect just that tiny bit of distortion through that whole chain, that would be quite cool. So the first thing we have to do is data collection, pre-processing. It's the main part of doing machine learning, is doing the data. The actual building the model is usually quite simple. So we've got to get audio into the application. I've shown you we can monitor both ends of the circuit. That's grand. We need to align the audio because we've got this issue that obviously it takes time to go through the circuit. We then need to convert it into frequency domain. We're going to do some dimension reduction, which I'll come to, and then we want to get it into decibels and the right sort of ratio, min-max scaling to not make sure it's not going all over the place, the values. So audio obviously takes time to get through the circuit. For the Radio 5 circuit I showed you, it's 30 milliseconds. It's not too bad. For the DAB full circuit, it's nearly 3.5 seconds. We can't do predictions of the output if our input is 3.5 seconds ahead. So we need to do some way to align the audio before we pass it further down the chain. And what you really do is you take chunks of audio of your samples and you multiply them together, your inputs and your outputs, and you add them together. And then you shift it by a sample and you do the same, and you look at the value where it's highest, and that's where it's mostly aligned, which would obviously take ages. So luckily, there's a mathematical formula called cross-correlation, which basically says if you convert it into the frequency domain, multiply them together, then convert it back out of the frequency domain, you can then find the highest peak there. That gives you the exact sample difference between your two things. So we do that, and we just buffer the input circuit by however many it is, so that they're now sample aligned. After that, we put it into the frequency domain. We take 2048 samples at a time, put it through a windowing function to stop spectral leakage, and we get an FFT out of it for both the inputs and the output circuits. That gives us 1,024 input variables per observation, as they call it, and 1,024 output variables per observation. That's quite a lot. We're trying to run it on a Pi. It's going to make our models very complicated. It's probably not going to run on a Pi with that many things. So we need to reduce the dimensions. So we could do something really simple. We could just go, rather take those 1,024 and let's just band every 10 together of those bins and just do an average. Or we could be a bit cleverer and we could use something called the MEL scale. MEL scale, short for the melody scale. It was some psychoacoustic analysis in the 20s, maybe? I can't remember now. It basically comes on the idea that if you think of when you listen to music and you go from middle C to an octave above, it sounds linear to your ear, but actually you've doubled the frequency. So it says humans listen to things in a logarithmic way, as well as volume, but also in pitch. And they came up with this scale. It's used loads in machine learning for speech analysis and stuff, MEL filter banks, MEL frequency coefficients and stuff. And the way you get from your FFT frequency to the MEL is you use things called MEL filter banks, which is basically just a load of triangular filters. And you take each triangular filter and you multiply all your FFT stuff with it, and you come out. It sums up the ones which are near to each other. As you see, as you go up the frequency, the filters get larger, so you get more of your frequency bins included in the same band. And from that, we can reduce our dimensions from 1,024 to 40. So now we've got 40 inputs and 40 outputs, which is much easier to handle. And that's what we're going to pass to our model to start trying to train our model. So a very quick thing on the software it's running on. This is the picture of the software it's running on. It runs on Linux. It's a virtual router, source plugins, output plugins, a little pin matrix thing, so you can go route that audio to that audio. It's got some real-time browser dashboard stuff. And for this, we wrote 3 new plugins. There's the audio alignment plugin, which I've spoken about, the frequency FFT plugin, and then finally the actual one which is doing all the work, the regressor plugin, as we've called it, because we're using regression. It does 2 different modeling types. It does linear regression, which is your line of best fit, your really simple one, and it does neural networks, which is your sort of be getting into your deep learning stuff with multiple nodes. When it comes down to it, each node is really just a linear regression model with another output function built onto it to provide some non-linearity. So how does it work? The audio comes in. The actual one we're using now is AES67 in. It was designed originally to be AES3, but we ended up using AES67 to come in. The audio comes in on 4 channels of AES67, 2 for the input, 2 for the output. They get monoed together and go to the audio line plugin, which then works out the difference between the input and output. Once it's worked it out, it sends the input and outputs to the regressor and says to the regressor, that little line at the top shows that, to start working. The first time you run it, the regression plugin starts gathering observations. It'll gather, on the live system, with the training's about half a day to a day's worth of observations. The examples I'm going to show was a couple of hours of observations. Once it's gathered all those observations, it then trains the model, so it either does its linear regression, find the best fit, or it does its backpropagation gradient descent neural network modeling. And once it's worked out the best model, it saves it to disk, so that if the program stops, or you can then take that model and put it elsewhere, the next time it starts up, it will load it from the disk. It then starts using that model on the inputs values to predict what it thinks the output values are. It's also got the output values coming in, so it can therefore work out the error between its predictions and the actual values. So you then get an error value, and that gets plugged into our alarm system to make an alarm to tell the people to wake up and listen to the audio. So how does it actually work? So these are some live results. Just quickly explain what these are. Each column is a different model. Ignore the one on the left because it didn't work at all. The one on the middle is just a simple linear regression. The one on the right, it's called the null model. It's basically just doing nothing. It says, I'm assuming the output's exactly the same as input. So it's just really to prove to myself that the middle one was actually learning something and was actually better than not doing anything. The two boxes, bottom box is showing the momentary error for each band. The top box, the red is the summed error, and there's a blue line, which is the average. It's rolling average over about 5-10 seconds, which is the actual value we lose for the alarm. So if I run this, you can see that middle one is not really coming off the bottom. There's no errors at all. It's predicting it almost perfectly. The one on the right is not very good. I'm not quite sure what happened with the left. It's also not very good. And then this is that faulty circuit that I showed you earlier for Radio 5. And as you can see, the blue line is now completely off the top. And what I quite like is that if you remember the way that looked, the averaging red bar looked, is pretty much the same as that the bar graph at the bottom looks as well. So the error you're seeing is exactly what you'd expect to see if it had learned the right things. And then Radio 1, this is the bit of audio I played with the clipping. This is the bit of audio without the clipping. So this is it's as if it was working. And this time, the middle one is still the correct one. The one on the left is now the wrong one, the one which is the null model. So once again, this is now a 2-layer neural network trained on about 4 or 5 hours of audio. It's again much better than not doing any learning. It's right at the bottom. And finally, this is now, once I've added that clipping, and again, even though you could hardly hear the fact it was clipped, the model says the predictions are miles out. It's completely wrong. Have a listen to it. So, conclusions. It works. For 5 Live, it works really well. Just with a linear regression model, it's actually, saying a linear regression model, it's actually 40 linear regression models, because each one only predicts one output, but it still works. The Radio 1, the simple linear regression didn't work at all, but a neural network of 2 or more hidden layers worked really well. Yeah, so hopefully you can see that you don't have to be Gen AI, you don't have to be sending off stuff to AWS. You can just use low-powered machine learning stuff to solve what seemed like intractable problems. That's it.